Hello everyone and welcome to Fatal Tech. As you might have guessed from the title of this video, we are going to see how to find a valid serial number or a valid license key for any Android application or program which is having client-side verification. Okay, many applications use license keys to control access to premium features or prevent unauthorized usage. However, some of these validation mechanisms can be bypassed if they are implemented solely on the client side. When an app validates licenses on the client side, it means that the validation process occurs within the app itself, usually on the user's device. The app checks whether the provided license key is valid by comparing it with the predefined rules or patterns, right? So if the key matches the expected format, the app grants access to the premium features or remove restrictions. Okay, so to demonstrate this, let's get started with this sample application which is already installed on my device over here. And when we launch the application, you can see that it has two input fields, license key 1 and license key 2. Based on this, we can assume that this application is expecting two valid license keys and accordingly it will unlock the features. Also, before moving forward, let's observe the behavior of the application, how it's behaving when we enter a wrong license key. So let me enter any random value and click validate, and immediately we can observe that the application is terminated. Alright, now let's directly jump into its analysis. So I have this sample application present on my system in documents training 2024 cracked license directory, and if I list out the contents, it has this app release.apk. Okay, and you can also download this sample application from my GitHub repository, link to which is mentioned in the description box below in case you want to play along with this application. Alright, so as usual, first of all, we need to extract this APK, and for that, I'm going to use APK tool decompile app release.apk. Now it's extracting the resources and files from this application, and once it's done, we have this app release directory created. So let's go inside it and see the contents. Alright, so it has all the resources and files which are usually there in any application. Alright, so this will be required later. So let's leave it like this for now. What we need to see right now is how the decompiled code of this application looks like. So for that, I am going to use JADX tool. So I have the JADX tool already configured in my environment variables, so I can directly launch it using JADX GUI command. Once the JADX GUI is launched, we can simply open our application, which is this one, under crack license app release.apk. Give it some time to decompile the application. Okay, so on the right hand side, we can see all the decompiled source code packages which are present in this application. And in the end, we have this resources directory where all the resources of the application is present. So let's first have a quick look at the Android manifest.xml file to understand what all activities and services are present in this application. So in this manifest file, we can observe that there are a couple of interesting things like these providers and receivers, but there is only one activity tag defined, which is having the launcher category. So this is our main activity which is getting launched initially when we are launching the application, right? So let's directly go to this main activity which is present inside this com.fatalsec.license validator package. We can navigate to this package from the left hand side pane. So over here we have com fatalsec.license validator, right? And if we expand it, we have our main activity. When you double click it, JADX will show you the decompile code. So over here, there are a couple of interesting things which we can notice. First one is that there is a static block in which system.load library is being loaded, and the name of the library is license validator. So if you know, a static block always gets executed first even before main function. After this, if you know how Android activity lifecycle works, usually onCreate method gets executed. So let's find this onCreate method which is present over here. So under this onCreate method, we can see that there is a set onClick listener callback present, and inside onClick we have a switch case statement where based on the value present in this i4 variable, it will decide whether to call this method or this method, right? Now if you go back to the application and observe the UI, we can see that there are two validate buttons, right? So basically what's going on over here is if the first validate button gets clicked, case 0 will be executed, and if second validate button gets clicked, P method will be executed. Okay, so let's see what's inside this O and P methods. If we double click on it, it will take us to the definition where this O method is defined, which is here. Over here, we can see that there is a if condition, and if this if condition is true, it telling that license validation is successful. Otherwise, if this if condition is false, then this else block will be executed, and over here, it's telling that license validation is failed. Okay, so here actually the things are quite simple because there is no obfuscation present, at least on the Java layer. Now you might be wondering that we can simply create a Frida script and hook onto this function and replace its return value or set its return value to always return true so that the application consider it as a success. But instead of doing that, let's consider that it's a complex function, and instead of returning simple true and false, it returns something complex like a byte array or some random integer value. In such cases, it would become difficult to bypass license validation checks. So to overcome this situation, we have to dig deeper into this function, which if you double click on it, you can see that it's the native function taking a string as argument and returning a boolean value, right? So this native keyword here suggests that this function is not part of this Java package, but it's coming from a native library. And so far in this main activity, we have observed that there is only one library which is getting loaded in this static block, that is license validator, right? Similarly, we have another function, this one, which is also coming from this native library. So at this point, we can say that when we click on the validate button in our app, one of these function gets triggered. And based on the input value which we pass, it decides whether the license is validated successfully or not. Okay, so our goal here is to generate a valid license key and not just bypass this license validation check, right? So for that, we need to dig deeper into this license validator library and analyze these two functions to see what's going on inside these in order to extract a valid license key, right? And if you don't know, this license validator library or any native library in Android application resides under this lib directory, then this particular application is designed only for ARM64 architecture. So we have this ARM64 directory, and inside this you can see that we have this lib license validator.so file. So let's analyze this native library. Let me go to the directory where we have this native library present, which is under app release, which we earlier extracted using APK tool, right? So over here we have this lib directory, and inside this lib directory we have to go inside ARM64 v8 directory, and here we have lib license validator.so. Now for analysis, I am going to use Radare this time, but you are free to use any other disassembler of your choice like IDA, Ghidra. Okay, so to open this native library in Radare, we have R2 command followed by the library name, hit enter. So now this native library is loaded into the Radare, but it's not yet analyzed. So to perform a deep analysis, we have to pass a command called A, but to perform a deep analysis, we have to pass 6 times A. Okay, so the analysis is now done by Radare, and to list out the functions, we have AFL command. Over here we can see that we have these two functions present, right? Now to see the disassembly of the function, what we have to do, we have to change the cursor to point to this function. So this function is present at this offset in this native library. So we can simply copy it, and using S command we can seek to that offset. So now you can observe that from this address our cursor has moved to this offset. So now basically the cursor is pointing to this function. Okay, now to see the disassembly, we have to pass pdf command, which simply says print disassembly of the function. Hit enter, and that's it. This is the disassembly of this function. The function look pretty simple. At the top we have couple of instructions which are basically used to store the arguments of the function, followed by a function call which is bl function 74c. So this function looks interesting because after doing the initial setup, this function is calling out this function. So probably this is the function where the real logic of license validation is written. So let's go to this function again by using s command followed by the symbol name or the offset. In this case, I am using the symbol name which is assigned by Radare during the analysis, which is fcn.74c. Hit enter and now we are at 74c offset, right? Now to see the disassembly again, we have to pass pdf command, and this is the disassembly of this function. At first, this looks a bit flat. I mean, to your eyes, it might look complex. So let's visualize it better in more graphical way. So for that, if you type vv command and hit enter, it will show you the control flow graph of this function, right? So now we have this nice looking control flow graph, and now it becomes little easier for us to understand like how the flow of this function is going. Okay, so in this first block, we can see that it's calling strlen function, and then using cmn instruction, it's comparing the length of the string passed in this function. If the condition is true, then it's going directly to the end of this function where it is calling exit function. So based on these instructions, we can say that the first check is based on input length, which we can figure out from these two instructions. Basically, after this strlen function call, the result of this function will be stored in x0 register, right, as per ARM64 calling convention. Then using this subtract instruction, it's subtracting the value hex 3d from the value present in x0 register, and then finally storing the result into x8 register. Then using cmn instruction, which stands for compare negative, it compares the value in register x8 with hex 14. But it's important to note here that it's actually adds the value of x8 register with hex 14, and based on the results it will set either zero flag or carry flag. Okay, then finally we have this b.lo instruction, which stands for branch if lower. It checks if the carry flag is set or not from the result of the previous instruction, right? And accordingly it will decide which branch to take. So now we have a mathematical equation here, and if you apply some reasoning, you will be able to find the length of the input, which will be able to satisfy this condition. All right. But this is not our goal here, and manually solving such instructions would be very time consuming and next to impossible in a big complex application having more complex logic. So this was about this block. Similarly, if we scroll down and come to this block, we can see that it's having compare branch on 0 instruction. And similarly, what we can observe here is that almost all the basic blocks present in this function are having some kind of comparison instruction in the end, right? So for example, in this basic block, we have this CBZ comparison instruction, where CBZ stands for compare branch on 0. This means that if the value in W8 register is 0, then it will go to this offset, which is this one, hex 77C, right? Otherwise, it will take this branch and come over here. Okay, similarly, you can analyze rest of the basic blocks. So there are a lot of possible combinations which can be made over here, right? With each block, a different set of path can be taken. Let's see what do we have in the end. So in the end, we can observe that there are two blocks. If we try to evaluate this particular block right before the end block, we can see that if the values in x8 and x9 register are not equal, then this exit block will be executed. Otherwise, this return block will be executed. So this is what we have observed initially when we entered the wrong license, right? The app got terminated immediately. This means that we have to avoid this exit block from being executed so that our app does not terminate. Now let's take a step back again and see what will happen if the value in these x8 and x9 registers are equal. So if the values are equal, this branch not equal to condition will become false, and this false branch will be taken and it will execute this return block. which means that the function is ending here, but before returning, it's putting 1 in this W0 register. So in the beginning, in our decompiled code, we observe that the functions are returning Boolean values, right? And according to ARM64 calling convention, the return value of the function is always stored in X0 or W0 register. So here basically by setting 1, it's trying to return true from this function. Now based on this analysis, we can say that we have to provide the input string in such a way that it always ends up here in this block where it's returning true, and make sure to avoid this basic block where the app is getting terminated because of this exit function call. Also, one more thing we can observe from this CFG is that there are total 4 places, 1, 2, 3 and 4, from where this exit block can be reached. But there is only one path to reach the valid return block. And also another interesting thing is that there is no hard-coded string present. So the whole logic of license validation relies on some mathematical computations, right? So at this point, we can say that manually identifying the correct serial key is not possible even in this small function, which is not even obfuscated. So you can imagine in real world applications how complex it would be to manually extract or figure out a valid license key. Now you can obviously use the debugger and attach the breakpoint to all these comparison instructions to somehow reach to this correct return block, but this will not give you a valid license key. Our goal here is to have a valid license key which we can pass as an input in the application to unlock the features, right? So to solve such problems, we have a very powerful framework called Angr Framework. So if you Google about this Angr Framework, this is the first link where it says that Angr is an open source binary analysis platform. It combines both static and dynamic symbolic analysis, providing tools to solve a variety of tasks. So these are the different features. Okay, so you can go through the documentation of the Angr framework if you are interested in getting started with it, and also let me know if you are interested, so that I can create a separate series on Angr framework itself to show you its usage and how you can use it in various reverse engineering tasks. Okay, so this Angr framework basically internally uses Unicorn emulation to emulate the code to solve a variety of problems, and it can also be used to solve satisfiability problem like this one, where we have to satisfy these conditions in order to reach to the correct block. Okay, so now to get started with this Angr framework, let me quickly open up my Visual Studio Code and open the folder where I have this crack license directory present. So this is the APK and this is the extracted directory, and over here I am going to create a script called keygen.py. Okay, firstly, make sure that Angr is installed on your system. If not, then you can easily install it using pip3 install Angr command. And for every new project, it's always good to create a new virtual environment so that the dependencies will not get conflicted. So for this crack license project, let me create a new virtual environment using Python 3-m virtual environment, and then the path where I want to create this virtual environment, which is inside this current directory with the name virtual environment. Okay, hit enter, and now you can see that a new virtual environment directory has been created here. Now to activate this virtual environment, we have source command, then virtual environment bin activate to activate this environment. Now you can see here that the virtual environment is activated. Now in this environment, I am going to install Angr using pip3 install Angr. It will download all the required dependencies which are required by Angr framework. So once the installation is done, we get this successfully installed message. Let's clear the terminal now. And now we can simply import the Angr package in our script using import Angr. Now in the application, we have to find two valid license keys, license key 1 and license key 2, right? Let's create a function called solve1 to solve the first license key. Okay, so in this method, first of all, we need to load the library, which is liblicense_validator.so in this case, in the Angr framework, right? So let's see which API is required. What we can do, we can open up the Angr homepage and go to the docs. So Angr documentation is pretty good and detailed, and you will find most of the required information over here to get started with Angr framework, right? So our first step is to load the binary. So we have this loading a binary documentation. Now you can go through the documentation in detail, but I'm just going to use the APIs which are required. So to load the binary into the Angr framework, we have this loader API which is angr.project, right? So that's what we are going to use. After importing the Angr dependency, we can simply type angr.project, and as you can see, this function takes one argument which is the path of the binary. So our binary is present in this extracted app release directory under libarm64, right? So we can pass this path app release lib arm64 v8a lib license validator.so, right? And this API returns an object which we can store into a variable, let's say p. All right. And there is another optional argument which I want to use here, which is called just a second, let me try to find it. Backend summary, yeah, this one, auto load libs. So basically, if this flag is set to false, then it basically tells Angr framework to not load the third-party libraries on which this native library depends on. So basically, it will not resolve the symbols which are coming from third-party or external libraries. So to set this option, we can pass auto load libs and set it to false for now. So now our binary is loaded by the loader of the Angr framework. So this loader in theory works exactly like a real loader in operating system. So whenever we execute any application or binary, the loader of the operating system basically loads it into the memory at certain memory address, right? So similarly, the loader of Angr framework loaded this library at some address which we call base address. So to find out where this library is loaded, what we can do, we can use p.loader dot main object dot minimum address. So this will give us the base address where the library is loaded. All right. This is important because we need to find the exact addresses of certain functions or blocks in which we are interested in. Next, after loading the binary into the Angr framework, we have to define a new state, or we have to tell Angr from where to start executing. So for that, if we go back to the Angr documentation, we have this machine state. Basically, a state in Angr represents the complete snapshot of a program's execution at a specific point, and it includes information about program's memory, registers, and other relevant data. Now, if you want to start executing from the beginning of the binary, you can use the entry state API directly. Or there is another state called as blank state where you can tell Angr to start execution from a certain offset. Okay, so that's what we are going to use over here. So to create a new blank state, we can use p variable, and then we have a factory member where we have this blank state API defined. And in this blank state, we have to pass the address from where we want to start the execution. In this case, because we are solving the first license key, which is this particular function, right? So this function is getting started from 74C offset, right? So that's why the address which we have to pass over here is 0x74C. But this is the offset and not the actual address in memory after loading the binary into the Angr framework. And for that reason, we have calculated this base address here. So what we have to do is add this base address to this offset so that we have the real address in memory after loading. All right, let's save this state into a state variable. Okay, so it's now like telling Angr that you can start execution from this address, and by default this blank state gets initialized with minimum required information. What it means is that the memory and registers are not initiated and they are basically blank as of now. Now from the decompiled code, we observe that this function takes a string argument, right? So as per ARM64 calling convention, the first argument of any function is stored in x0 register followed by x1 and x2 and so on, right? So what we can do, we can create a symbolic variable for storing the input key. So like I said, the first argument of the function, which is the input key in this case, is going to be stored into x0 register by default in ARM64 calling convention, right? But instead of using the concrete x0 register, we are going to create this symbolic variable. So let's see in Angr how this symbolic variable gets created. So if we go back to the documentation and under the symbolic expressions and constraint solving, you can see that it has this symbolic variables. What basically a symbolic variable means, instead of saying that a variable has a concrete numerical value, we can say that it holds a symbol, effectively just a name. Then performing arithmetic operations with that variable will yield a tree of operations. Okay, so basically symbolic variables allows Angr to explore different execution paths through a program, and by branching on symbolic conditions, Angr can analyze how program behavior changes based on different inputs or conditions. Okay, so to create a new symbolic variable, we have this solver attribute inside the state object. So to create a new symbolic variable, we have this API called state.solver.bvs, where it creates a bit vector symbol named x of length 64 bits, right? So in our case, we have the state variable over here. So to create a new symbolic variable, we can use state.solver.bvs, and it takes two arguments. First one is the label. Let's call it as serial, and then the other one is the size. So let's consider that the key maximum key length is going to be 1024 bits. So we can define it like this. Okay, and let's put this bit vector symbol into a variable called arg. Now we need to store this bit vector into the memory. So for that we need to first define some random address. So let's put random address 000000, let's say 41 41 41 41. Okay, so this is the address I am going to use to store this bit vector serial. Okay, and to store it into the memory, we have a state.memory.store API, and again it takes two arguments. First one is the address and second one is the symbolic variable which we have defined here. Okay, once this is done, now we have to set x0 register to hold a pointer to this address as first argument, right? Because as of now we have just created a new symbolic variable which is stored in the memory at this address, but the x0 register, which is the register used by the function for storing the input key, that is still a register, right? So we have to point that register to this address so that the input argument will act as a symbolic variable. Okay, so for that we have state.add constraints method, where in this we can pass the constraint and basically tell where x0 should point to. So the x0 register we can access using the state.registers.register name, which is x0, and we are strictly going to tell that it should point to this address. Okay, so this we have added as a constraint into this state which we have created over here. So in summary, here we are telling that x0 register should point to this address, which is a symbolic variable. So now this symbolic variable will contain our first argument. Then we need to create a simulation manager in Angr. So the simulation manager is a crucial control interface which allows you to manage symbolic execution over groups of states simultaneously. And its primary purpose is to explore a program's state using various strategies. And we can basically move forward, backward, or even move between different states. So once the constraint and initial state is configured, we can start exploring the solution. So let's see how we can create a simulation manager. So for that we have the simulation manager's documentation over here, and using project.factory.simmanager we can create a new simulation manager. So let's do that. Here we have p.factory.simulation manager. All right, and this takes one argument which is state itself. Okay, and this we can store into a simulation manager variable. And like I mentioned, we can step forward, backwards, and even move between different states via simulation manager. So all of that we can do using this SM variable now. So now once the constraint and initial state is configured and the simulation manager is initialized, we can simply start exploring the solution using simulation manager.explore API. Okay, and this basically takes two arguments. First one is the find argument. This argument specifies an address that the symbolic execution aims to reach. So during the analysis, we observed that we have to somehow reach to this block, right, which is present at hex 7ed. So this is going to be the find address, and like I explained earlier, this is the offset which needs to be added into the base address, right? And then the second argument is going to be the avoid address. So over here you can actually pass multiple addresses if there are multiple blocks which you want to avoid into the array like this, but for this example we only want to avoid one block, which is this exit block. Okay, and the address or the offset where this avoid block is present is 7f8. So let's put it like this and add our base address to this offset. Okay, so actually you can leave this explore function like this, but I would like to add another optional argument called enable vary testing to true. This basically tells Angr to combine multiple paths into a single path which shares same constraints. And this is very useful to eliminate path explosion problem which usually occurs in Angr when we try to explore various paths in a big function. So in summary, this way we are telling Angr to find a solution which leads us to this offset and avoids this address. So once the exploration is done, we will get a new state which we can store in a variable called found. Okay, so basically this explore function explores various paths in order to reach to this address while avoiding this address. Okay, and as a result of this we will get a new state. Now there could be multiple states. So to store the state, let's create a variable called found, sm.found 0. So the found variable now holds a state that satisfies the specified condition during symbolic exploration. This state represents a successful execution path that reaches the address we are searching for. Okay. Now we can further analyze this state to extract relevant information or perform additional tasks based on the program's context. Now to print the solution, we can use again the solver attribute to evaluate the symbolic expression, which is arg in our case, right, to obtain the concrete value. So for that, in found variable we have the new state, hopefully with our solution. So using found.solver.evaluate function, we can evaluate the result of the exploration. And like I said, the result should be present in this arg variable. So the first argument of this evaluate function is the arg argument, and this we want to cast as byte. Okay, So this is going to be the answer, and let's extract the result from this answer like this. So basically here, after getting the answer in the form of bytes, we are eliminating the null characters if there are any, and then simply storing the result in this out variable. Then finally, all we need to do now is print the results. So raw string output, let's print it using the format specifier out. Okay, so this will print out the result. Let's save the script at this point and try to run it once and see what do we get in the output. But before running, we need to call this solve one function, right? Like this. And over here we have this keygen.py script which we just created. So to run it, we are simply going to execute python 3 command followed by keygen.py. And you can observe that there are some warnings thrown by the Angr framework, which is totally fine. It's just saying that there are some memory and registers which are not initialized, and that's because we have created a new blank state with the minimum information, right? So give it some time, because depending on the complexity of the function, it tries to evaluate various possible paths to reach to the solution which we have requested for, right? So for this small function, you can imagine how many possible permutation and combinations can be made to reach to this particular block. And that's exactly what this Angr framework symbolic execution does. So obviously this is going to take some time. Alright, so the execution is done, and in the end we can see our raw string output, which is WZB. This should be a valid license key. Let's try to copy this and put it in this license key 1 field, right? Let's click validate, and boom, we got the success message. Cool. So we have found a valid license key to unlock the application features, right? Now you might get different key because there could be multiple ways to reach this block. Okay, cool. Now let's try to figure out the second license key. So for that, again, we can go back to the Radare terminal. Let's come out from this visualized mode. Okay, and again list out the functions. So earlier we analyzed this one. This time for the second license key, we have this function over here which is present at this offset. So let's seek to this address, and now our cursor is pointing to this A2C, and to see the disassembly of this function we have to run pdf command, hit enter. Unlike the previous one, this time we don't have that branch to another function, right? So basically this is the whole logic for second license key validation. And like earlier, let's switch to the visualized mode using vv command. So over here, actually we can observe similar stuff like the previous one. There are conditional instructions present in each block, right? Then at the end we have the exit block and the return block, and inside this return block it's storing 1 into w0 register, which basically returning true from this function. So just like the previous one, we have to avoid this block and we want to reach to this correct return block, right? So what we can do in our script, create a new function called solve2. Okay, and we can simply copy paste this whole code, right? And we just need to change the blank state and the exploration function. So we want to start execution from this function, right, which is present at A2C. But note here that instead of starting from this A2C function, we will start from this address where this move x19, x0 instruction is present, and that's because this is a JNI function and Angr is not able to execute JNI functions from the beginning. So we will skip the initialization part of this function. So right before this move x19, x0 instruction, you can observe that there is a branch instruction where it's trying to call another subroutine. And in ARM64 calling convention, we know that the return value is stored into X0 register, right? So whatever the return value written by this routine will be stored into X0, and using this move instruction, that X0 value will be stored into X19 register, and then the whole license validation logic executes. Okay, so to get the offset of this instruction, let's switch back to the normal mode, print the disassembly. So this move instruction is present at 84C. So let's change this blank state to 84C, and we want to find the address of the return block, which is this one, 8B4, X8B4, and we want to avoid the exit function, which is present at 8BC. So this is going to be 8BC. Let's save the script and call this sol2 function. This we have already evaluated, so I'm going to comment it and simply going to call sol2 function. Clear the terminal and let's try to run the script. All right, so we got the output. Let's copy it and see whether it's a valid license for the second license key or not. So I'm going to simply paste it, and if we click on validate, we got the success message. Cool. All right, so using Angr Framework, we managed to find valid license keys, and you can basically apply more or less the same logic, where all you have to figure out is the find address and the avoid address, and also the place where the user entered keys being stored. Like in this case, it was in X0 register, right? So once you have these information, you can configure everything in your script and let Angr explore the right solution for you. I hope you found this video useful. If so, then don't forget to hit the like button and share it with your friends and colleagues. Also feel free to comment in case you have any questions or doubts. Thank you, and I will see you soon in the next video.